In this statistics section, we will be talking about probability distributions. We're going to talk about how do we know what a probability distribution is. We're going to talk about how we can use the probability histogram. We're going to talk about how do we know whether data that we are discussing is going to be significantly low or significantly high. So quite a bit to cover in this section. All right, let's start with some definitions. A random variable is a variable, and they will always refer to it as X in this textbook, that a single numerical value determined by chance for each outcome of a procedure. The distribution will be a very nice little chart that tells you for each instance. So if there's 0 outcomes, it'll give you a probability that that happens. If there's 1 outcome, it'll give you a probability of that happening. So it's very nice. It will be either a table or a formula of some kind, but usually we'll be talking about tables. A discrete random variable is a collection of values that is finite. It means we can count them. It will not be something weird, like if we can count the number of heads that we toss. A continuous random variable is something that has infinitely many values, like body temperature can vary. I mean, just depending on the technology we're using, it can get very, very precise. So there's really not everybody is 98.6 degrees. You may be 98.611. You may be 96.599. You might be. So those we would call continuously random variables. All right. How do we tell when we get a chart if it is a probability distribution or not? So first of all, your X will always be a number. It will not be a category. So that's one thing you should look for. And it will have those X's in the first column and then their corresponding probabilities in the next. If you add up all the probabilities, they should equal 1. If they add up to 0.999, that's acceptable. If they add up to 1.001, that's acceptable as well, because there might be some small rounding errors, but it will be extremely close to 1, if not exactly 1. And the probability in that second column, every value will be between 0 and 1, because we all know that probabilities are between 0 and 1. So here is an example, and we're just going to kind of walk through it to talk about the number. If you're having 2 children, the number of female births. Now, contrary to popular belief, there is not a 50% chance. There actually are more males born than females. Not very many, but the probability of having a male is actually 0.512, not 0.5. But for the sake of this exercise, we'll just say that it's 0.5. So this chart tells you that if you have 2 children, if you have 0 females, you have a 25% chance of having 0 females if you have 2 children. If you only have 1 female, that's a 50% chance, and if you have both are females, that's a 25% chance of that. So the question becomes, is this a probability distribution, and if so, how do we know? All right, so we're going to walk through the 3 terms. So the first term that had to be, all of our X's had to be numerical, which they were, 0, 1, and 2. The next condition was that all of the probabilities had to add up to 1, and that was 25% for 0 females, 50% for 1 female, 25% for 2 females. So add those up, and they added up to 1. And each of those probabilities that we had were between 0 and 1. So it does meet all the criteria to be a probability distribution. So we can say that this right here, and another thing that we can talk about is the fact that because this random variable 0, 1, 2, these are finite amounts. So these are discrete random variables that give us these probabilities and together add up to this lovely probability distribution. So this is a very short example. This is what the histogram looks like for this exact probability distribution. So this would be its corresponding probability histogram. Notice 0 births, 25%, 1 birth that was a female, 50%, both births were female, 25%. So this histogram should match perfectly the probability distribution. Now, there are many formulas that can be used. This is the probability formula that you would use to come up with this particular probability distribution. Now, there are many formulas, so don't think that this is the only formula we're going to have. This just happens to be the formula they use to calculate this. And we will talk about that in future lessons, how this formula came about. There actually is a reason. So stay tuned, and we will talk about that later on. But for now, we're just going to focus on identifying these probability distributions. So this is a software piracy chart. So if you'll notice, it has the countries listed, and then it has the proportion of unlicensed software. Okay, so the question is, does this describe a probability distribution? So remember, the first rule was that all of our x values, and that's our first column, all of our x values had to be numbers. And notice, these are categorical. So this is not a probability distribution right off the bat. I know that. Number two, your probabilities have to add up to 1. And if you notice, our total added up to 2. So that is another reason that this is not a probability distribution. And each of these probabilities has to be between 1 and 0, which it is, but it doesn't satisfy the other two requirements. So this is definitely not a probability distribution. So I already went through those 3. All right, so it's important to remember that your probability distributions are always going to be describing a population and not a sample. So just keep that in mind. And we can use these probability distributions to discuss means, standard deviations, variances. That will all be parameters, but we will never discuss statistics, right? Because we're talking about populations. We are not talking about samples. So here are the formulas to find. If you have a probability distribution, you can find the mean, the variance, and the standard deviation. So this next right here is our list of all of our formulas that we're going to need. So the mean is very simple. You're just going to add up all of your x's times your probabilities. So multiply those and then add them all up, and there you go. That's your mean. Pretty straightforward. Now, finding variance is a bit more complicated. This formula right here is the one that's much easier to calculate if you're having to do it on paper or doing it in Excel or StatCrunch or whatever. So that's the one that I use quite often. You can use this one as well. This is the actual formula. It makes more sense when you're talking about what variance is, right? Because it's the difference of the square of the distance from each data point to the mean. But to calculate that, that's a bit more complex. So I definitely like to use that second one for variance. And then once you have this variance, to find the standard deviation is quite easy. You just take the square root of whatever that is. Because we know that the standard deviation is just squared is the variance. So definitely keep these in mind. They are also on your formula sheet, so you don't have to worry about remembering them. The expected value of a discrete random variable is just denoted by the capital E, and this is also the mean. So anytime they say expected value, it's the same thing as saying the mean. So again, if they ask you to find the expected value, you would just add up each of your random variables multiplied by their probabilities and just add all those together. All right, so let's walk through an example. So we can go back to our example where we had the number of female births. So if they asked us to find the mean, the variance, and the standard deviation, I would kind of tell you to just make a little chart. It's probably the easiest way. So this is the chart that I use. So if you want to find the means, you're just going to add up the x's times this. So here, 0 times that, doesn't matter, that's still 0. 1 times 0.5 is 0.5. And then 2 times 0.25 is 0.5. So add these all up, and that adds up to 1.0. So that is going to be your mean, right? So your mean is going to, for this, and your expected value. Which expected value for this means if you were to have 2 kids, what is the expected value of female births? So if you have 2 kids, the expected value is to have 1 girl and 1 boy. Not that other things can't happen, but that's what's expected. All right, if you wanted to find the variance and the standard probability, that's where this would come in. And again, I'm going to be using, this is the original chart that you should use. So for each point, you're going to take the variable minus the mean and square it. So 0 minus 1, right? Here's our mean. So 0 minus 1 is -1. 1 squared is 1. And then multiply that by 0.25. And that gives you 0.25. And then you're just going to repeat that over and over again. So 1 minus the mean is 0. So that would be 0 squared, which would just be 0 times 0.5. Well, anything times that would be 0. And then 2 minus the mean would be 1. And that's going to end up being exactly the same as that up there. So if you look, that would mean our variance is 0.25. And then if you wanted to find the standard deviation, that would just be the square root of 0.25, and you would just put that in your calculator, whatever that is. 0.25. Sorry, I added those up wrong. A quarter times a quarter is a half. Sorry about that. So that'd be half, so this would be the square root of a half. So you could just put that in your calculator. So this just means that, again, the mean is the expected value. So the mean number of females in 2 births would be 1. The variance is 0.5 females squared, which doesn't even make any sense from a practical standpoint. And the standard deviation, when you take the square root of that, is going to be about 0.7. So the standard deviation is 0.7 females. And again, this just means that if we were to ask 10,000 people who had 2 kids how many females they had, that on average it's going to be 1. Yet one of the 2 children is going to be female. So that's just an example of how you can just make a chart and do all that. Now, if you're using any kind of statistical software, it'll do all this for you. So it kind of makes it all moot, but it's kind of important to know how to do it because we will be doing it like this when we take the test and when you're doing your homework and that kind of thing. All right, so again, to know if your results are significantly low or significantly high, you're just going to be looking for your data values to be greater than 2 standard deviations away from the mean in either direction. So if they're above the standard, if they're above the mean, more than 2 standard deviations, that's going to be significantly high, and then below would be 2 below the mean, 2 standard deviations below. So if we look back at our last example, we knew that the average, the mean was 1.0 female births out of the 2 with a standard deviation of 0.7. So are those results, considered, is the results that we achieved to be low or high? So if we look at the range, right, so if we look at mu plus or minus 2 standard deviations in this case, our mu was 1 plus or minus 2 times 0.7 was our standard deviation. So 1 plus or minus 1.4. So on the high side, you'd have to have more than 2.4. Well, you can't have more than 2.4 births if you've only got 2 kids, so that is nonsensical and doesn't even make sense. And then 1 minus 1.4 would give me a negative number, right? So that would also be nonsensical. I can't have a negative number of children. So none of the things that we found here would be considered significantly high or significantly low in this case. If you are looking for a significantly high number of successes in your trials, it's considered a significantly high number of successes if the probability of X or more successes, and that's the big thing, significantly high if successes that your probability of X or more is less than 0.05. And 0.05 is not rigid. It could be 0.01 depending on what you're doing, but it's X or more. Just keep that in mind. And if you're looking for significantly low, it's X or fewer is less than 5%. And again, that 5% might be 1%, it might be 2%, just depending on what you're doing. So keep that in mind as you're working on these. The rare event rule for inferential statistics is that given under any kind of assumption that you're making, the probability of a particular outcome is very small, and the outcome occurs significantly less or significantly greater than what we expect with that assumption. So our assumption could be wrong, but if we get the data that says, oh, you're way off, then we're definitely going to assume that we were wrong to assume that in the first place. So for example, we assume that there's a 50% chance that you have a male or a female when a woman gives birth. But for example, if we were testing the assumption that males and females, so that was equally likely, and the outcome for 20 females in 100 births was significantly low. If we had the outcome that for 20 males, 20 females in 100 births was significantly low, then maybe we would say, oh, you know what, maybe we were wrong to make that assumption that the males and females are equally likely. So kind of important that you keep that in mind. As we said before, our expected value will just be like calculating the mean. So let me give you an example of how we can use expected value. Gambling is an excellent way to talk about probabilities. So we're going to talk a lot about gambling in this chapter. So you have $5 to place on a bet at the Gold Nugget Casino in Las Vegas. You have narrowed your choices to 2 different bets. Number 1, you could go to the roulette wheel and bet your $5 on number 7. Or you could go to the craps table and bet your $5 on the pass line. Now, you don't really have to know anything about these 2 games. We're just going to do expected values. So we're going to look at the first example, that if you bet that $5, and then we're going to look at the dice game of craps. Okay, so it says, if you bet that $5 on the number 7 in roulette, the probability of losing $5 is 37 out of 38. Because there's only one number 7 on that roulette wheel, and the other 37 are not the number 7. 37 slots on that roulette wheel. So the probability of making a net gain of $175 is 1 in 38. Okay, so this is the prize. You would get $180, but you obviously didn't spend the $5. You spent the $5, so your net gain was only $175. Find your expected value of what that $5 bet would be. All right, so we're going to walk through that, and then we're also going to do the same thing for the game of craps. So when you're playing craps, the probability of you putting your $5 in the pass line and losing is 251 out of 495. And don't worry how they came up with that. They're just telling you what it is. And the probability of you making a net gain of $5, so you would win your bet and you would win your $5, is 244 out of 495. And again, those are net gains. You know, they're taking out the fact that you use the $5 to begin with. So we find the expected value for that. Okay, so the easiest way to do this is to make charts. So I have charts already set up. So we have to fill out the chart with the X, the probability of that happening, and then remember to find our expected value, you have to add up the X's times the probabilities. All right, so the probability, so our event X is that we lose. Now, if we lose, we're going to lose $5, right? Because that's what we bet. They told us that we have a 37 out of 38 chance of losing. So multiply those 2 together, and that gives you negative $4. And I'm going to go way too many decimal places. Okay. Now, if you win, you're going to win big. You're going to win $175. Right? And that you only have a 1 in 38 chance of that. So that gives you expected value of 4605263. Again, it's positive. So if you want to find your expected value, you just add those 2 together and you get negative, and I'm going to round it to the nearest penny. Okay, so that's negative 26 cents. So that means if you play roulette over and over and over and over and over and over and over, just betting on that number 7, even in the long run, right, you're going to lose money. You're going to lose 26 cents over time. So again, doesn't really make sense to play. Well, it doesn't make sense to play any of these games, to be honest. But all right, now we do the same thing for craps. So if we lose, again, remember, we're going to lose our $5 if we bet on the pass line and we don't win. And that has a probability of 251 out of 495. Multiply those 2 together and you get negative 2.535353, just keeps repeating. But if you win, you're going to win $5, and that has a probability of 244 out of 495. Multiply those 2 together, you get positive 2464646. Add those up, you get negative 0.07. So you would lose much less money by playing the craps. Notice you're losing both. This tells you, this is why the casinos make all this money, is because they set up the games so that the expected value is that you are constantly losing money. And that's really important that you understand. Every single game at the casino is set up this way, that you will lose money. They do that on purpose. Okay, so which one is the better bet though? Definitely craps, because your expected value is much lower. Even though you're still losing money, you're losing much less money than if you were to play roulette. So Hope this helps a little bit when you're working on your practice. So please go practice, and I'll see you in the next lesson.